channel Chemistry Drive with Nujmun Nissa. How are you students? You are preparing for term 2 exams. So you must have prepared some of the chapters for term 2. This is one of your chapter, that is coordination compounds, lesson number 9 in your book. And I hope this chapter and this video also will help you in improving your, you can say, the studies related to coordination compounds. So students, let's start with our chapter. Coordination compounds. What are coordination compounds? These are the additional molecular compounds, and the one important thing about it is that they retain their identity in the solid state as well as in the dissolved state. So actually how these coordination compounds look like, suppose I am taking this compound K4Fe CN6, okay, this is a compound, okay. Now this thing, the structure that is enclosed in the square bracket is a complex ion. So such type of a compound in which you can see a central metal ion that is bonded to the ligand with the coordination bond, such type of compounds, they are known as coordination compounds. And definitely we are discussing what are the coordination numbers, coordination sphere and the effective atomic number in this video. The next one is double salts. Now what is the difference between double salts and coordination compounds? Double salts, they are also the additional molecular compounds. They are stable in solid state but they dissociate into ions in the solution form. So we'll look at its example, that is Morse salt. It consists of iron sulfate and ammonium sulfate along with 6 moles of water of crystallization. So when it forms in the dissolved state, it just dissociates into its ions, Fe+2, ammonium ion and sulfate ion. So such type of salts that get dissolved in the solution form, they are known as double salts. Example, Morse salt. The next one is complex ion. What is a complex ion? It's an electrically charged species. As the name suggests, it's an ion. So it may be a positively charged ion or may be a negatively charged. It is surrounded by a number of ions or a neutral molecules. For example, if I just write it like this, such type of an ion, it is known as complex ion because it is surrounded by number of ions that are known as ligands. Next one is cationic complex entity. If the complex ion is positively charged, then it is a cationic complex entity. For example, tetra-ammonium platinum ion, it's a positively charged species. And if you look at the anionic complex entity, then you will be like, we are taking the example. So since this complex ion has a negative charge, so it is a anionic complex entity or negative ion, negative complex ion. Now what is central atom or ion? Suppose in this compound, this is, we are taking nickel chloride having another ligand, water. In this, you can see there is a central atom nickel, okay. Then it is connected with coordination bonds with chlorine atoms and with water molecules. So it is bonded to the anionic species as well as with the neutral molecules. Such type of a metal that is bonded to the different type of ligands with the help of coordination bonds, it is known as the central metal atom. I hope it's clear. The next one is ligands. As I have just told you, ligands, they are the electron donating species. They donate the electrons to the central metal atom ion, and we have seen its example also. In this example, we have seen that there are two types of ligands in this complex. chlorine and water, they are donating their electrons to the central atom, that is nickel. Now ligands, they are of different types. Number one is unidentate ligand. What is a unidentate ligand? It means a ligand that has only one donor site. It is known as a unidentate ligand. For example, water. It gets attached to the central metal ion with only one site. Ammonia. It also joins through nitrogen atom, the lone pair that is present on the nitrogen atom. So, the ligands having only one donor site, they are known as unidentate ligands. The next one is didentate or bidentate ligands. We'll take an example of oxalate ion. In the oxalate ion, you can see it has two donor sites. That is here CO negative, this one and this one. So it is a didentate ligand. Similarly, we can also take the example of ethylene diamine. It has two donor sites. That is the lone pair of electrons that are present on the nitrogen atom. They act as the donor sites. So ethylene diamine is another example of didentate ligand. The next one is polydentate. What is polydentate? More than two sites. Any ligand that provides more than two sites for forming coordination bond with the central metal atom, it is known as polydentate ligand. That is adita. Its example is adita. Here you can see each nitrogen atom has one lone pair of electron and they are bonded to acetate ion. So this is the example of a polydentate ligand. As you can see, as it's clear in the picture, that it has more than two donor sites. It can donate electrons either from this side, this one, and finally these are the sides through which it can bonded. It can get bonded to the central metal atom. So that's why it is known as polydentate ligand. Now what is ambient ligand? Any ligand that has more than two donor sites. For example, we can see this is NO2 negative, okay? It can donate, it can get attached itself to the central metal atom either through nitrogen or through oxygen. So it has two donor sites. So in one form it will be attaching itself to the central metal atom as Na2, and in the other form it will be attaching itself through oxygen in the form of nitrite. So here you will use the word nitro for that, and there you will use the word nitrito for that. That we will be discussing in the nomenclature of coordination compounds. The next one is chelating ligands. That is the di or the polydentate ligands. The ligands that we have just discussed, they are the example of chelating ligands. That is the ligands that having more than two sides to be joined with the central metal atom. So here we can see that's what we have seen in the case of adita. In the case of adita, we have seen, what is adita? It is ethylene diamine tetraacetate ion. So it is a polydentate ligand, as we have discussed earlier, as well as it is chelating ligand. That is the ligand that have more than two donor sites. I hope it's clear. Next is coordination number. So here we will be discussing about what is coordination number in case of complex ions. So it is defined as a number of coordination bonds that has been formed with the central metal atom ion. It is known as the coordination number. So let's have a look. at an example. Suppose this is a complex ion. Okay. As you see that platinum is linked with 6 chlorine atoms. So how many bonds a central metal ion is being formed with the chlorine? That is 6. So its coordination number will be 6. I hope it's clear. So coordination number is the number of coordination bonds that has been linked with the central metal ion. For example, in the case of polydentate ligands, so many of the number of the coordination compounds that has been formed by the polydentate ligands, that will be the coordination number of that central metal ion. So you should take care of this thing. Now what is coordination sphere? That is, there is a central metal ion. It is linked with the ligands. So the central metal ion as well as the ligands, the whole complete the family of this is known as the coordination sphere. That is, we'll have a look over it. This PT is linked with 6 chlorine atoms, okay? This whole structure that has been bounded in the square brackets, it is known as the coordination sphere. The next one is the oxidation number of the central metal atom. As you have discussed in your 11th class also regarding the details of oxidation number, that is how we can find it out. Let's see. This is tetracyanocopper and it has a charge of -1. So how will we finding out the oxidation number of, its charge is -3. So how will finding the oxidation number of copper? We'll take copper. The sign on cyanide ion is -1. The total charge being -3, that is put after equal to sign. Then we will getting it as, so the charge on the copper ion we are getting as +1. So in this way we are going to calculate the oxidation number of the central metal ion. If there is, the charge is equal to 0, that is the complex ion has no charge, then you have to put 0 here. Okay. Types of complexes. There are 2 different types of complexes, homolaptic and heterolaptic. Now what is homolaptic? If the ligands, they all are similar, that is the ligands that are bonded to the central metal atom, they are all similar, then it is homolaptic. And if the ligands are of different types, then it is heterolaptic. For example, we'll take the example of, here you can see 6 ammonia molecules has been bonded with the cobalt. So all the ligands, they are of same type, that is ammonia. So it is a homolaptic. It is homolaptic. Now if the ligands that are bonded, they are of different types. For example, here you can see we are having 2 different types of ligands, that is ammonia and chlorine. So they are of different types, so it is a heterolaptic. The last one is the effective atomic number. This concept actually it was proposed by Sidgwick. Now in a complex, the effective atomic number of a metal ion, it is equal to the atomic number of the element minus its oxidation number of the metal, oxidation number of the metal, and plus 2 multiply by the coordination number of that metal ion. So this is how we are going to calculate the effective atomic number. Once again, how will you calculate? Z denotes the atomic number of the central metal ion. So first you will take the atomic number of the central metal atom, then you will subtract the oxidation number of the metal ion, then after that you will add the coordination number multiplied by 2 to the whole sum, and you will be getting the effective atomic number. So students, thank you. Keep watching my video. In my next video, I'll be discussing about the nomenclature of organic compounds.